Alright, this video will be on how to solve an integral using U-substitution. We're going to do examples that include definite integrals and indefinite integrals. We are evaluating the definite integral secant squared of 5x plus 1 times 5. And we're going to solve this using U-substitution. Inside of the integral, in these parentheses here, I see 5x plus 1. I'm going to set u equal to 5x plus 1. U is set to 5x plus 1, and now we need to find du. In order to find du, we have to take the derivative of what we set u to. So we need to find the derivative of 5x plus 1. Personally, I like to think of du as derivative u, because that signifies that you're taking the derivative of u, and that's how I remember it. Alright, now, how do we take the derivative of 5x plus 1? Well, the first thing that we want to keep in mind is the sum rule for derivatives. This here is the sum rule for derivatives, and it's saying that if you're taking the derivative of one function plus another function, it's equal to the derivative of the first function plus the derivative of the second function. We're going to keep this in mind because we're going to take the derivative of each term and 5x plus 1 separately. Now I want to be very clear with this notation here. This is f prime of x, and this is g prime of x. What this little apostrophe here means is that you took the derivative of the function. So f prime of x is the derivative of f of x, and then g prime of x is the derivative of g of x. Like I stated previously, when taking the derivative of 5x plus 1, we're going to go term by term. So let's evaluate the first term here. What's the derivative of 5x? In order to take the derivative of 5x, we need to apply something called the constant multiple rule for derivatives. Written out here below the sum rule is the constant multiple rule for derivatives. It's saying that if you're taking the derivative of a function that is multiplied by a constant, right? So a constant multiplied to a function, it's going to equal that same constant multiplied to the derivative of that function. So with 5x, we have 5 multiplied to x. Here, 5 is considered the constant and x is considered the function. So really what we need to do is take the derivative of x alone. Then we'll multiply back 5 to the derivative of x. For clarity, I wrote out 5 times the derivative of x. How do we take the derivative of x? In order to take the derivative of x, we need to apply something called the identity rule for derivatives. This here is the identity rule for derivatives, and all it's saying is that if you're taking a derivative of a variable, it's always going to be 1. So the derivative of x is going to be 1. We have 5 times 1, and 5 times 1 equals 5. Next up, we're going to take the derivative of our second term. How are we to take the derivative of 1? In order to take the derivative of 1, we're going to apply something called the constant rule for derivatives. Written out here is the constant rule for derivatives, and all it's saying is that if you're taking the derivative of a constant, denoted with a c, it's always going to equal 0. A constant is any number. It can be 1, it can be 5, it can be 25, it can even be a fraction like 1/2. But in our case, we have 1 as our constant. So the derivative of 1 is going to be 0. Let's now turn our attention back to the sum rule. Because the sum rule says that the derivative of one function plus another function equals the derivative of the first function plus the derivative of the second function, that means it's going to give us the answer for the entirety of the operation. In other words, the derivative of 5x plus 1 is going to be 5 because that's what we found for the derivative of 5x, plus 0 because that's what we found for the derivative of 1. Our answer, 5 dx. Allow me to clean this up just a bit. Because the derivative of 5x plus 1 equals 5 dx, the derivative of du is going to be 5 dx. Dx means that we just took the derivative. Moreover, if you ever see a dx attached to a function, that means it's the derivative of something. Allow me to clean this up a bit. At this point, we have u and we have du. So what we'll do now is substitute that into the integral. We have our integral sign, and then we're going to bring down that secant squared because we haven't done anything to it yet. We're just going to substitute u for 5x plus 1, and then we're going to substitute du for 5x. Now that we've done U-substitution, we're going to evaluate this integral. Let's take a look at the secant squared. There are integration trigonometric rules, and there is a rule defined for secant squared. This is the trigonometric integration rule for secant squared. It says that the integral of secant squared of x is equal to tangent of x plus c. C here just means constant. So we can see that this looks awfully familiar to what we have in our integral. Using this rule, we'll evaluate the integral. We followed this formula exactly. So now we have tangent of u plus c. What we need to do now is back substitute for u. What that means is plug in what we had for u into the function, 5x plus 1. And then plus c. You add that plus c when you're dealing with indefinite integrals. This is our answer. Tangent of 5x plus 1 plus c. All right, I like that. Let's do another one. This here is the definite integral from 3 to 5 of 2x minus 3 over the square root of x squared minus 3x plus 1. So to solve this, we're going to use U-substitution. How do we find du? We need to find the derivative of x squared minus 3x plus 1. We can do this by going term by term. So let's look at term 1. In order to find x squared, we're going to apply the derivative power rule. This here is the derivative power rule. It says that when you're taking the derivative of something that has an exponent, you're going to bring the exponent out front, and then you're going to multiply it by the base, and then you're going to keep that same exponent there, but you're going to subtract it by 1. So in this case, our exponent is 2, therefore our n is going to be 2. We brought our exponent out front and then we multiplied it to our variable. Then we raised it to the same power, only we subtracted 1. Therefore, the derivative of x squared is going to be 2x dx. Now we're going to do term 2, negative 3x. How can we take the derivative of negative 3x? Well, negative 3 is a constant, and then x is a function. So we're going to apply the derivative constant multiple rule. Here we have the derivative constant multiple rule. The constant in this case is going to be negative 3. So we'll have negative 3 times the derivative of x. To take the derivative of x, we'll apply the identity rule for derivatives. Remember, the derivative of any variable by itself is always going to be 1. As it turns out, this is going to become negative 3 times 1, which is just negative 3, or negative 3 dx if you will. Now let's work on term 3. What's the derivative of 1? Well, if you recall from earlier, we can apply the derivative constant rule. The derivative constant rule says that the derivative of any constant is always going to be 0. Since we're taking the derivative of 1, and 1 is a constant, the answer is going to be 0. Now what we're going to do is we're going to add up the derivatives for terms 1, 2, and 3. We'll find that if we add up all of the terms together, we're going to get 2x minus 3 dx. This is going to be our du, so I'll write this up here. Now what I'll do is I'm going to clean this up. Since this is a definite integral, we need to evaluate at our new bounds. And we'll do so using u equals x squared minus 3x plus 1. Let me show you what I mean. So as we can see here, our lower bound is 3. And u, being set to x squared minus 3x plus 1, is going to be what we plug 3 into. 1 is going to be our new lower bound. So we're going to replace this 3 with 1. Next up, we're going to evaluate our new upper bound. Our upper bound here is 5. So we're going to plug in 5 to x squared minus 3x plus 1. The answer is going to be 11. That means that 11 is going to replace this 5 because it's our new upper bound. So here's our new integral. We're replacing the lower bound 3 with 1. The lower bound is now 1. We're replacing the upper bound 5 with 11. The upper bound is now 11. We can now plug in our substitutions. On the bottom here we'll have u, and then on the top we'll have du. Du over the square root of u is the same thing as 1 over the square root of u times du. I'm going to make some room here. We'll need to do some mathematical manipulation here. Let's remember the rules of exponents. This is the rule of exponents that we're going to want to keep in mind. See how in the index we have n, and then underneath the radicand we have x. This is the same thing as x raised to the power of 1 over whatever's in the index, n. Let's apply this to what we have. We have a square root of u, and that's going to be the same thing as u raised to the power of 1/2. Now we have the integral from 1 to 11 for 1 over u raised to the 1/2 power. Now we want to mathematically manipulate this again, and we will use another rule of exponents. This says that if you have a fraction and there's something that's being raised to a certain power in the denominator, you can actually bring that up, but you have to make the exponent negative. Let's apply that here. 1 over u raised to the 1/2 power is the same thing as u raised to the negative 1/2 power. We can change our integral again. We now have the integral from 1 to 11 for u raised to the negative 1/2 power. What I'll do now is clean this up. There's something very particular that needs to be done when you're evaluating an integral for something that's raised to a power, and it's called the integration power rule. The integration power rule says that if you're taking the integral of something that's raised to a certain power, you can do so by taking what you are raising the power to, raising it to that same power, but adding 1, and then putting that over the original exponent plus 1, but that's going to be in the denominator. Pardon me, this should have a dx here. Let's now evaluate this integral. Remember that every number has an invisible 1 underneath it, unless explicitly stated otherwise. Right, so if you see nothing under a number, you assume that there's a 1 underneath it. But how can we add fractions together that don't have a common denominator? You can change the denominator to match the fraction you're trying to add or subtract to, or you can find a constant multiple of the two and find the lowest common denominator. But in this case, I can just change the denominator of 1 over 1 to 2 by multiplying it by 2. But what you do to the bottom, you have to do to the top, right? And then I could do the same thing down here, multiply the denominator by 2, but then I also have to multiply the top by 2. Okay, now we can add the numerators together and keep the denominator the same. Okay, now what we have here is called a complex fraction. We do not want this. So what we'll do is we're going to take the reciprocal of what's in the denominator and we're going to multiply that to the numerator. Okay, so we found the answer to be 2u raised to the power of 1/2, but we're not done here. Because this is a definite integral from 1 to 11, we're going to introduce something called the evaluation bar. And the evaluation bar is going to have a 1 on the bottom, since that's the lower bound, and it's going to have an 11 on the top, because that's the upper bound. I'll make some space. Okay, so the way to read this is 2u raised to the 1/2 power, evaluated from 1 to 11. So we're going to evaluate the bounds here, and we're going to do so by applying the fundamental theorem of calculus. This is the fundamental theorem of calculus. And so pretty clearly, we can see that this format matches what we have. But what does the right side of the equation mean? It means that you plugged in the limits of integration into the function. So these capital F's mean that you plugged in b and a into the function, and then you subtracted a from b. So allow me to exemplify. So let's work through this, and then hopefully this will be a little bit more clear. 1 here is going to equal a, and 11 is going to equal b. So to properly apply this, we need to plug in what we have for b into the function. So 2 times 11 raised to the 1/2 power. Then we need to subtract whatever we get from when we plug in a to the function. So 2 times 1 raised to the 1/2 power. So if you're still confused as to why these F's are capital, take a moment to review this format and try to understand that they only become capital after you plug in whatever the limit of integration is that you are putting into the function. So for the upper limit of integration gets put into the first term, right? And you plug that into the function. Then the lower limit of integration gets subtracted from the first term, and that's going to be whatever you get from plugging a into the function. All right, so I do need a bit of room here, so I'm just going to move these out of the way. And I'm going to bring this up because now there's a rule for fractional exponents and radicals that we need to apply. So all three of these things mean the same thing. It's just switching forms. Okay, so if you have something that's raised to a fractional power, the denominator for that fractional power can be put into the index of a radicand, and then the base of the exponent is going to be raised to the power of what you originally had in the numerator, which is also the same thing as taking the original denominator or index and then plugging that into a radicand over originally what you had the base set to, and then raising the entire thing to the power of what you originally had the numerator into, or what you had the base being raised to underneath the radicand. So we have 2 times 11 raised to the 1/2 power. We're going to evaluate the exponent first, okay? So that 2 is just going to come down. We're going to leave that alone. The 11 raised to the 1/2 power, the base is 11, so that's what's going to go underneath the radicand. The denominator of the fractional power that it's raised to is 2. So that means that we are going to put a 2 in the index. All right, and now what's in the numerator for the fractional exponent is 1. So Really, we're raising 11 to the power of 1. Okay, but 11 raised to the power of 1 is 11. So technically we don't have to write anything, but because we want to be very meticulous and show what's going on, we're going to write that there. The same way that there's a general concurrence that if you just write a radical, you're taking the square, but we wrote the 2 in the index anyway. So now for our second term over here, we're just going to take the 2 and we're going to bring it down. Now the base of what we have the fractional exponent attached to is what's going to go underneath the radicand. Okay, so the base here is 1. The denominator for the fractional exponent is 2, so we'll put a 2 in the index. And then because there's a 1 in the numerator of the fractional exponent, we're going to raise it to the power of 1. So what this will become is 2 times the square root of 11 minus 2 times the square root of 1. Do you see how there's a 2 that's attached to both terms on the outside? We're going to factor that 2 out of both terms. Now, I left the 1s in front of the radicands because I wanted to show that we took the 2 away and then the 1 is all that's left there, but we can actually simplify further. And we can't simplify anymore after this, so this is going to be the answer to our problem. 2 times the square root of 11 minus the square root of 1. Cool. Let's try another one. We're going to evaluate the indefinite integral of x raised to the third power times cosine of x raised to the fourth power plus 2. Now, since we're solving this with U-substitution, we have to figure out what we want our u to be. What can we set u to? In these parentheses, I see x raised to the fourth power plus 2. That's what we're going to set u to. Now we need to find du. How can we find the derivative of x raised to the fourth power plus 2? Let's take the derivative of the first term, x raised to the fourth power. Since we're taking the derivative of something that's being raised to a power, we're going to apply the derivative power rule. Written in blue is the derivative power rule. So let's apply it. X is being raised to the power of 4. So we'll bring the 4 out front, multiply it times the base of it, then we'll subtract 1 from the original exponent. This leaves us with 4x raised to the third power dx. Now we'll take the derivative of the second term, 2. Since 2 is a constant, the derivative of 2 is going to be 0. Now we'll add the derivatives of the first term and the second term together. What we'll be left with is 4x cubed dx. 4x cubed dx is going to be du. Wait, but we have u set to x raised to the fourth power plus 2, and we see that in our integrand. But what we don't see is the derivative of x raised to the fourth power plus 2. We do not see 4x cubed dx in the integrand, and that's a problem. However, what we do see in the integrand is x cubed and dx. X cubed dx is a constant multiple of 4x cubed dx. Perhaps I can make this a little bit more clear. What I did was I moved the x cubed over so it's out in front of the dx now. We have x cubed dx, which again is a constant multiple of 4x cubed dx. Because 4x cubed dx is a constant multiple of x cubed by 4, we have to put it in terms of x cubed since that's what we are replacing in the integrand. So here's what we'll do. We're going to divide both sides by 4. So now these 4's will cancel. We have du over 4 equals x cubed dx. Du over 4 is the same thing as 1/4 du. Now we have a match because we do see x cubed dx right here. So we can replace it with 1/4 du. Now we'll replace u for x raised to the fourth power plus 2, and we'll replace x raised to the third power dx with 1 over 4 du. Lovely. So now what we'll do is we'll factor out the constant. The constant here is 1/4. We're going to take it out of the integrin. We'll move forward with evaluating the integral. There's a trigonometric integration rule for evaluating the integral of cosine of something. This trigonometric integration rule says that the integral of cosine of x is going to equal sine of x plus c. So since the integral part is going to become sine of u plus c, we need to multiply back the constant. So really we're going to have 1/4 times sine of u plus c. The only thing left to do is to back substitute what we had for u, which was x raised to the fourth power plus 2. So instead of putting a u, we're going to put x to the fourth plus 2. And this is going to be our answer. 1/4 sine of x raised to the fourth power plus 2 plus c. And remember, we're adding the plus c because this is an indefinite integral. This question says, evaluate the indefinite integral of the square root of 2x plus 1. So how can we solve an equation like this? Well, with U-substitution, of course. What can we set u equal to? Well, underneath the radicand here, I see 2x plus 1. That's what we'll set u to. Now that we've set u equal to 2x plus 1, what will du be? Well, du will be the derivative of 2x plus 1. So how are we to take the derivative of 2x plus 1? To take the derivative of 2x plus 1, we're going to go term by term. The derivative of 2x is going to be 2, because it's a constant, times the derivative of x. What's the derivative of x? Well, the derivative of x is just going to be 1. So we have 2 times 1 equals 2 dx. The derivative of 2x is going to be 2. So next up, we are going to take the derivative of 1 because it's the second term. If you remember from before the identity rule, when you take the derivative of a constant, it's always going to be 0. The answer, 0 dx. Now what we're going to do is we're going to add together what we found for the first term and what we found for the second term. 2 plus 0 is going to be 2. So the derivative of 2x plus 1 is going to equal 2. All right, now here's where it gets interesting because we found that the derivative of 2x plus 1 is going to be 2x. Therefore, du is going to equal 2 dx. However, when we look at our integral here, we don't see 2 dx. We see dx. Therefore, we need to manipulate this. What we need to do is divide by 2. We'll divide both sides by 2 and find that these 2's cancel. Then we have du over 2 equals dx. Now this is the same thing as saying 1/2 du equals dx. So up here, du is 2 dx, but 1/2 du is going to equal dx. And now now another way to write this is, we can factor out that 1/2. And of course, another way that we could write this is not factor out that 1/2, but bring it out here in front of the square root of u. And now we can apply the square root rule for integrals. Please note that 1, 2, 3, 4 are all the same equation. It's just manipulated. All right, now check this out here, because this is the square root rule for integrals. Here, A is 1/2 and T is U. So let's apply this. All right, so now we have the indefinite integral of 1/2 times U raised to the power of 1/2. Okay, so now what? Now what we'll do is we'll apply the power rule for integrals. This right here is the power rule for integrals, okay? So our x is going to be u and our n is going to be 1/2. So what I'll do is I'll make a little bit of space. And now what I'll do is I'm going to factor out that 1/2. All right, and this will become 1/2 times u raised to the power of 1/2 plus 1 over 1/2 plus 1. All right, and if you're confused here, just remember that every 1 has a 1 underneath it. Every number has a 1 underneath it. So we'll put a 1 underneath here, and now we need to make these addable, so we'll multiply the top by 2, we'll multiply the bottom by 2. Then down here, we'll multiply the top by 2, and then we'll multiply the bottom by 2. And that's how we got here. So now at this point, we have a complex fraction which we don't want. So we will take the reciprocal of the denominator and multiply it to the numerator. The reciprocal of the denominator up here is going to be 2/3. And now we'll just multiply this through. Remember, because this is an indefinite integral, we're going to add that plus c at the end. Okay, and I brought this up here because all that's left to do is back substitute for u. Now this here will be our answer. 1/3 times 2x plus 1 raised to the power of 3/2 and then plus c. This is our answer.